Hello there. Today's 16.3. Our goals are to graph polar equations and define intersections of polar equations. We'll take a look at a few examples here, starting with the first here. This is a table of r values and theta values. Keep in mind that polar coordinates will be in the order r theta. Oftentimes, theta is the dependent variable and r is the independent variable, x and y. So our ordered pairs are r theta, but often we're given the theta instead of the r, just worth keeping in mind. So what we'll do here for 6 cosine theta, you can see the theta values are given and the r values are calculated. And then in this particular table, they flip the order to make the r first and the theta second. So the first ordered pair here would be 6, 0. Then I'd have 3 root 2 along with pi over 4, keeping in mind that pi over 4 is a 45-degree angle and 3 root 2 is the length of the radius. So what that would do is actually make the ordered pair right there at 3, 3. Next, we would have 0 along with pi over 2. Radius of 0, we'll put that right at the origin. The next point would be negative 3 root 2 along with 3 pi over 4. Keep in mind that this length here was 3 root 2. So negative 3 root 2 is this way, maybe a little bit more than 5, and then rotated 3 pi over 4. That's going to put us right here. Negative 6 is this way, rotated pi is going to bring us right here. Negative root 3 over 2, 5 pi over 4 is going to bring us back right here. And you should notice that we've got a repeating pattern here. Turns out that this particular polar equation gives us a circle with a radius of 3. And that's going to be something worth taking a look at here as we move forward. So one of the things we want to be able to do is make a table and plot points to make a polar graph. A couple of things here worth remembering. A polar equation, r equals a. If r is fixed, r is a given value, we are going to get a circle that is centered at the origin. So r equals 7 is going to be a circle centered at the origin with radius 7. Okay, so those are some basic ones. If it's just got an r in it, it's got a fixed radius. A polar equation, theta equals a, and we talked about this a little bit the other day, but the polar equation theta equals a is a constant angle. So it's a line contains the terminal side of that value. So if I have theta equals pi over 4, we are going to have an angle of pi over 4, a line going through that. Okay, that's something we briefly touched on the other day that's worth remembering as we move forward. Here are some examples of some common polar graphs, and we'll take a look at a couple of these. I recommend you throw in some A values and some B values into your Desmos to take a look, but circles are commonly going to take on the form r equals a sine theta or r equals a cosine theta, and if we go back up here, this one was a cosine theta, 6 cosine theta to be exact. So 6 cosine theta gave us a circle, radius 3. So common polar graphs that are circles are going to have a constant value in front of a sine or a cosine. Don't need to memorize those, but we'll have this to refer to as we go through the rest of this lesson. What just popped up on the screen here is an example of a cardioid. And a cardioid, if it involves a cosine curve, is going to be kind of like a sideways looking heart. If it involves a sine, the cardioid is going to be more of a vertical looking heart. It's kind of like circular, but it's got a bend in the inside. So cardioids kind of look like that. The key to a cardioid is that the a and the b value here are the same. So r equals 7 minus 7 cos theta is going to give you a cardioid. That's what this little qualification here is where the A over B ratio is equal to 1. So 9 plus 9 sine theta, those two values being the same, would give you a cardioid. Now added to your screen over here are some examples of lumicons. And lumicons are similar to cardioids, other than, well, instead of A and B being the same value, the same absolute value, the A and B value is different. So you can see the red graph here has an inner loop. The green graph here also has an inner loop. The orange one is dimpled, and the blue one is considered convex. These are not things you need to memorize, but those A values and B values are really worth playing around with if you want to make cool looking polar graphs, which not necessarily useful in real life, but could be pretty fun to make some pretty cool cardioids and lumicons. And next we'll talk briefly about rose curves. Here are some color-coded examples of rose curves. You can see that the orange curve here has an R value of 3 and has an A value of 3 and an N value of 2. As we change the R value to something bigger like 5, you'll see that the rose petals get extended. And the green one has a value of 1, which makes that radius, so to speak, smaller. So the larger that lead coefficient is, the longer the petals will be. And the value inside the cos, or the sine, will impact the number of petals. You see that the blue curve has 5 petals. The orange curve has 4 petals, and the green also has 4 petals. So you can play around with those and make some pretty cool graphs. Again, these are some things that are worth being familiar with, but not something that you're going to be held to high stakes. Let's talk about, now that we've talked about some cool graphs, let's talk about what you're going to need to be able to do for your test next week. The first thing is you need to be able to complete a table given some theta values to find some R values. So with your function r equals 2 plus 2 cos theta, we are going to put in the given theta values to find r values. I'll go ahead and complete that table. You can go ahead and pause the video and complete that table on your own, and we will compare values in just a moment. All right, I've filled out my table, and I hope you've done something similar. You will notice that this is a cardioid graph. 0, 4 is right over here on this graph. 0, 4, radius of 4, angle of 0. Pi over 4, that ends up being 2 plus the square root of 2. Pi over 2 goes with 2. 2 pi over 3 ends up having a radius of 1. And 0 pi. Now we could continue. You don't need to continue this graph, but you will end up having a pretty similar pattern going out this way to complete that table. So that's something you'd be able to do. Graphing a couple of those points is extremely useful if you are able to do so, but that's kind of the thing which you're going to be looking for our test tomorrow. The test is not tomorrow, the test is next week. The next thing we're going to look at is we're going to algebraically find intersections. And the caveat to this that we always need to consider is that we're going to need to check for an intersection at the pole, and the pole being 0, 0. Those will not show up for us algebraically, so we got to play around with that. So here's what we're going to do. Here's a system of equations. And as we talked about before, if we have x's and y's, we use a process of substitution to find solutions. So what we're going to do here, because both of these expressions are equal to r, we're going to set them equal to one another. So I'm going to go 1 minus 2 sine theta equals 2. Subtract the 1, I get negative 2 sine theta equals 1. I get sine theta equals negative 1/2. Go ahead and take a look. Sine theta equals negative 1/2. Looks like to me at 7 pi over 6 and 11 pi over 6. If we keep going, we could have additional coterminal angles there, but we're going to go with 0 to 2 pi. And those are our theta values. So I'll say theta equals 7 pi over 6 and theta equals 11 pi over 6. Now for intersections, we want locations, and we're going to go ahead and we could substitute theta in for the sine value to find out what the radius would be, or we could use a little common sense here and know that our radius is 2. So our two intersections that we know of right now are 2 7 pi over 6 and 2 11 pi over 6. It is worth checking and considering for an intersection at the pole, the intersection being 0, 0. For this particular problem, though, we know that r equals 2 is a circle that has a radius of 2, so there will not be an additional intersection at the pole. Take a look at example 3. So we will go ahead and set, we're gonna need to solve for r here. So r is plus or minus square root of 2 sine 2 theta. And we'll set that equal to 1. So we'll say plus or minus square root 2 sine 2 theta equals 1. At this point, I might actually do something different here. I might just go ahead and set up two different equations. Okay. We will square both sides here. Let's start with this first equation. Square both sides. We get 2 sine 2 theta equals 1 squared. We can move the negative 1. Let's stay with this equation. We're going to stay on this side for now. Okay. Sine 2 theta equals 1/2. Okay. Up above, we knew sine theta is 1/2 at pi over 6 and 5 pi over 6. So we will say that 2 theta equals pi over 6 plus 2 pi k. So theta would be pi over 12 plus pi k. We also know that 2 theta could be equal to 5 pi over 6 plus 2 pi k. So theta would be 5 pi over 12 plus pi k. All right, so our theta values between 0 and 2 pi are going to be from this one. We're going to get pi over 12. We're going to add pi to that, so that would be 13 pi over 12. If we add pi again, we're going to get 25 pi over 12, so that's too big. From this second equation, we're going to get 5 pi over 12. And if we add pi to that, we're going to get 17 pi over 12. Okay, so these angle thetas, shouldn't put a box around it yet, but those angle thetas are going to be part of our solutions. Now we'll take a look over here at the right-hand side. Divide both sides by -1. I get square root 2 sine 2 theta equals -1. Hope you realize a problem right here. You can't get a negative value when you square root, but let's just say for fun that we did. Square both sides and you get a 1, which is the same equation that we solved over there. Okay, so our intersections now, radius is 1, and the thetas are going to take on those values. So 1 pi over 12. 1 13 pi over 12, 1 5 pi over 12, and 1 17 pi over 12. Also worth checking for an intersection at the pole being 0, 0. Since the r value is 1, there's not going to be a point on that circle at the pole. So let's take a look at a graph of those two functions just so we can verify our solutions. Here's a look at a graph of those two functions. Worth noting here that there is the second equation with the r squared was split up into two different functions. This function is not showing on the graph, but it is identical to the red one. You can go ahead and graph that on if you feel like it. Worth noting, all of the solutions have a radius of 1. That's on the green circle. Pi over 12, 5 pi over 12, 13 pi over 12 and 17 pi over 12 represent our points of intersection. At this point, I'm going to ask that you go ahead and complete the homework. We've got a couple of complete the table questions. I will go ahead and post an answer key to this on Schoology. We've got some intersections. Whenever you get intersection questions, you want to check for an intersection at the pole. Okay, there may be a problem or two here where you have an intersection at the pole. So 6 problems of homework to do. Check Schoology for updated office hours and availability. Hope all goes well, and we will see you soon. Thanks.